Well, Science 10s, we just finished talking about pendulums and the law of conservation of energy. So here we are, video 3 on the mechanical energy note guide. We had just been talking about how a pendulum moves and there's a transformation of energy. And for our example, we are going to consider that all of the potential energy that the little bob, the little pendulum has at the top is going to be entirely converted into kinetic when it reaches the bottom and vice versa as it reaches the top. So, to help understand a little bit, I have this nice little video that will show us what happens. So, here's the bob, and we can see that as it moves, the kinetic energy goes up. And when it reaches the top at the other side, it's not moving anymore, but it's maximum of the potential energy, or EP or PE as is written here. So here it's mechanical is all potential. It's not moving. There's no kinetic energy. As the object's moving, kinetic energy goes up, it reaches its maximum at the bottom, and then as it continues to go up, now it reaches its maximum potential energy. Okay, so again, understanding this transfer of energy, right? All of the mechanical energy at this point is equal to potential because there's no kinetic, it's not moving. When the bob reaches the bottom of its arc, all of the mechanical energy is equal to kinetic. Okay, there's no potential energy because there's no height. It's not above zero or above the ground. Okay, so here mechanical is all potential. As it starts to move, notice the kinetic energy, or EK, is going up. It reaches its maximum down at the bottom here, and so all of the mechanical is equal to kinetic. And then as we saw, it continues moving up. And once it reaches its maximum over on this side, same thing. All of the mechanical energy is equal to potential. It's not moving anymore. Kinetic is zero. And so at that point in time, all of the mechanical is equal to the potential. Okay, so the energy is going up and down. It's going from potential to kinetic to potential and back again. And so again, we're considering, because of this law of conservation of energy, that there is no energy loss due to any sort of friction or heat. We're just assuming that it's a perfect transfer of energy. And we know that's not real life, but for our energy calculations, that's what we're going to have to make an assumption. We're going to have to assume that. Okay, so let's do an example practice problem of a pendulum. Okay, so here we've got this pendulum, and we're given the mass of the bob, okay, or the little metal ball, and it's 500 grams, so we know its mass. And it's suspended on a string, and it's pulled horizontally and up a distance of 10 centimeters, and then you let go of it, you release it. At the bottom of the arc, the mechanical energy is 0.491 joules. So, guys, one of my great pieces of advice, my little saying, besides formula, substitute, math it out, do your final answer, is when in doubt, draw it out. So, let's draw our little pendulum. So, here we have the little bob, and we know the mass of the little bob. It's 500 grams, which of course we can do a unit conversion, 500 grams. We know the fact that 1 kilogram has 1,000 grams in it, and so we can convert, and that gives us 0.500 kilograms is the mass of this little bob. So we know how long the string is, but what is more important is how high it is above the ground, the height above the ground, because that's going to give us our potential energies, mass times gravity times height. So when we pull it off to the side like this, okay, my mechanical energy is equal to kinetic plus potential. We're holding it here. It's not moving. Because it's not moving, the mechanical is equal to the potential. So it's a maximum amount of potential energy. So the potential energy that we have at the top is the mechanical energy. Then when we let go of it, it's just going to start moving. And now the object is going to reach the bottom of its arc. And remember, mechanical energy is kinetic plus potential. So right now, there's no potential energy. This object is not above the ground anymore, but it's moving with its maximum speed. So our mechanical energy at the bottom is all kinetic. So EK at the bottom is where it reaches its maximum. So in other words, the kinetic energy that it was at the bottom should equal what the potential energy was that it had at the top. And it says at the bottom of the arc, the mechanical energy of the ball was 0.491 joules. So whatever it had at the top in potential was 100% converted into kinetic down at the bottom. So this mechanical energy is going to end up being all converted into kinetic. So we know the mechanical energy is 0.491 joules, and that's going to give us our kinetic, and we know kinetic is 1/2 mv squared. So what are we asking to find? We need to find the speed of the ball at the bottom of its arc. So what is the speed of the bob or of the ball once it reaches the bottom here? Well, we know that the mechanical and kinetic is equal to one another, right? They're transformed. We're assuming there's no loss of energy, so mechanical at the bottom is all kinetic. And so we know the mechanical energy. Can we solve for the speed? Yes, we've done a question like this before. Remember, we did EK is equal to 1/2 mv squared. We want to get v all by itself. We divide out 1/2 times m. Divide out 1/2 times m. Cancel both sides. Remember, you can leave it as this, or you can decide to go ahead and say, well, you know what, this is another way of writing this, is that 1 divided by 1/2 is 2 EK over m is equal to v squared. Almost there. We're looking for speed, not speed squared. So I want to take the square root of both sides. And when I do that, I find that the speed is the root of 2 UK divided by the mass of the object. We know the mass, we just convert it to kilograms. Now, we've got one more unit conversion to do here. Instead of writing 0.491 joules for our kinetic energy, we're going to have to convert joules to kilograms, meters squared per second squared. So when I divide by my mass in kilograms, I'll be able to cancel out that mass in kilograms, and then my units will be something root of meters squared per second squared, and that gives me meters per second, and that's the unit that I want for speed. Okay, so you, like you normally do, you've got your formula all figured out now. And like I say, when in doubt, draw it out. Draw a little diagram and ask yourself what's going on. Well, this is not moving. This is all potential energy at the top here. And when it does start to move, now there's no more potential energy. That's 0 when it reaches the bottom. The mechanical is entirely kinetic. So here I'm potential, and it got 100% converted into kinetic. Remember, we're using that assumption. We know that's not true in reality, but for our calculations, it's just going to work. Okay, so there is an example doing a pendulums. You can do the math on that one and figure out your answer. Okay, so again, draw it out, do your calculations. And so at the bottom of the pendulum, all the mechanical energy is kinetic. It's not got any potential energy, and EM is equal to EK at the bottom. Okay, now I want to do another question. You guys can do these other ones on your own. But I wanted to talk about number 8 here. So we've got an athlete jumping upward from the ground, and they've reached a height of 0.910 meters. Wow, that athlete can jump. That's almost a meter that they're jumping. I don't know who it is, but they're a pretty good athlete, not me. So here's the deal. When in doubt, draw it out. Oops, sorry, something happened. Okay, so here we have our little athlete. And our athlete at the bottom is got, it's jumping, right? So as the athlete jumps up, it's a second, the instantaneous that the athlete jumps off the ground, the kinetic energy is reaching the maximum. They're moving, right? And then once the athlete gets to the top and they're 0.910 meters higher than the ground, now they're reaching the maximum potential energy. Okay, and so we know that's mgh, and the kinetic is 1/2 mv squared. So what can I say? Well, I can say that the potential energy that this athlete has at the top was entirely converted from the kinetic energy that they had at the bottom. 100% unit conversion of energy, right? Remember, we're assuming this. We know it's not true in reality. There'd be energy loss to friction and heat, but this is our assumption. We know that mgh is equal to 1/2 mv squared. These are in our data booklet. We're understanding that the kinetic is entirely converted into potential. So what are we looking for here? We're looking for the speed. We're looking for v. Let's math it out. Okay, let's rearrange. I want to solve and I want to isolate. I want to get v all by itself. So first of all, I'm going to divide out 1/2 times the mass. Okay, oops, my pen is doing crazy things. Now, if I do that to the right side, guess what? Let's do it to the left side as well. 1/2 cancels, mass cancels. Excellent. Now, wow, look at this, guys. Mass is going to cancel off this side as well. Remember, you can leave it as 1/2 on the bottom, or understand that 1 divided by 1/2 is 2. Mass cancels. GH is equal to V squared. You all know this. We've done lots of practice. To go from V squared to V, I'm going to have to take the square root of both sides. So the root of 2 times the gravity times the height is V. So what's interesting here is we didn't even need the mass in kilograms. Okay, that wasn't even used. Do we know what gravity is? Absolutely. It's 9.81 meters per second squared. Do we know what the height is? We sure do. It is 0.910 meters. So you plug your values in and your speed is going to be the root of what's g? Well, it's meters per second squared times a height in meters. Meters times meters, meters squared over seconds squared. Root of that is going to give me my speed. It's going to be something meters per second. Okay, so understanding this law of conservation of energy is going to enable you, this is just a physics principle, understanding that you know how much potential energy an object has, it can entirely be, for our physics questions, 100% converted into kinetic or vice versa. Okay, so you guys will have some practice questions to do in this booklet, and you get a worksheet with extra more practice, so you can get really good at doing these calculations and energy conversions. All right, have a great rest of your day.